Hello and welcome. Tonight, we'll be exploring some of the most astonishing objects ever discovered in the universe. Cosmic giants that seem almost impossible to explain. Some are stars so enormous that they appear to stretch the limits of how massive a star should ever become. Others are black holes that somehow reached extraordinary sizes when the universe itself was still remarkably young. There are dazzling quasars that shine with the brilliance of trillions of suns, and immense structures so vast that they seem to challenge the way we imagine the cosmos on its largest scales. At first glance, these discoveries may sound like evidence that the laws of physics have failed, yet the truth is far more fascinating. More often than not, nature is not breaking its own rules. Instead, it is quietly reminding us that there are still chapters of the story we have not yet learned to read. So, find a comfortable place to rest, settle into a quiet moment, and let us gently begin our journey into one of the greatest mysteries in modern astronomy. When you look up at the night sky, it is easy to imagine that astronomers already understand most of what is out there. After all, humans have been studying the heavens for thousands of years. We have walked on the moon, landed robotic explorers on Mars, and built telescopes capable of seeing galaxies billions of light years away. It can feel as though the great age of discovery is behind us. But in reality, astronomy is still filled with surprises. Imagine exploring a vast forest with only a small lantern. Each step reveals another patch of ground, another tree, another winding path disappearing into darkness. The farther you travel, the more you realize that the forest is much larger than you first imagined. Our exploration of the universe is much the same. Every new generation of telescopes acts like a brighter lantern. Instead of confirming that we already know everything, these instruments often reveal landscapes we never expected to find. Sometimes those discoveries fit beautifully into our understanding of physics. Sometimes they do not. Scientists often have a special affection for these unexpected observations, not because they enjoy being wrong, but because history has shown that the greatest advances in science frequently begin with something that refuses to behave as expected. For centuries, people believed that all the planets moved in perfect circles around Earth. Careful observations slowly revealed tiny inconsistencies. Those small discrepancies eventually transformed humanity's understanding of the solar system. Much later, strange motions in the orbit of Mercury hinted that Isaac Newton's magnificent theory of gravity, while extraordinarily successful, was not the complete story. Decades afterward, Albert Einstein's theory of general relativity explained what had once seemed impossible. Again and again, science has progressed not by ignoring mysteries, but by listening to them. Astronomers sometimes refer to these surprises as anomalies. The word may sound dramatic, but it simply describes something that does not comfortably fit our current expectations. An anomaly is not proof that science has failed. It is an invitation to learn. And tonight, we will meet some of the universe's greatest anomalies. Imagine standing beside the tallest tree on Earth. Then imagine finding another tree twice as tall. Your first thought might not be that trees have changed. Instead, you would probably wonder whether you truly understood how trees could grow in the first place. Astronomers experience similar moments. They discover stars so massive that the intense light pouring outward should almost tear them apart. Yet somehow, these extraordinary stars continue shining. They discover black holes that seem to have become unimaginably heavy in what appears to be far too little time. According to our simplest models, growing that quickly should have been extraordinarily difficult. They discover brilliant quasars acting like cosmic lighthouses, illuminating the young universe long before many astronomers expected such powerful objects to exist. And then there are the largest structures of all. Vast collections of galaxies, stretching across distances so enormous that they almost seem to blur the boundary between individual objects and the architecture of the cosmos itself. Each discovery raises a quiet question: how? Not a question filled with panic, not a question suggesting that physics has collapsed, simply a calm, persistent curiosity. How did nature accomplish this? That question has inspired countless nights inside observatories, thousands of computer simulations, and decades of careful calculations by scientists around the world. Sometimes the answer turns out to be surprisingly simple. Sometimes it requires an entirely new way of thinking. And sometimes the answer remains just beyond our reach, waiting for the next generation of observations to illuminate another small corner of the cosmic forest. In recent years, that lantern has become brighter than ever before. The James Webb Space Telescope has begun revealing the early universe with astonishing clarity. Instead of finding a simple, quiet young cosmos, it has uncovered galaxies that appear unexpectedly mature, remarkably bright objects that challenge existing models, and mysterious populations of distant sources that astronomers are still working to understand. These discoveries have not overturned modern cosmology. Instead, they have reminded us that even our best theories are maps rather than the territory itself. A map is an extraordinary tool. It can guide explorers across mountains, rivers, and oceans. But every map is incomplete until someone walks a little farther and discovers land that no one knew was there. Astronomy has always been an act of updating the map. Every telescope extends the horizon. Every observation redraws another small piece of the unknown. And perhaps the most exciting discoveries are not the ones that confirm our expectations, but the ones that gently whisper that the universe is even richer, stranger, and more imaginative than we had dared to believe. That quiet realization prepares us for our first encounter with one of the most extraordinary inhabitants of the cosmos. Stars so immense that simply existing seems almost miraculous. Imagine standing outside on a cold winter morning, rolling a small snowball across fresh snow. At first it grows quickly. Each turn gathers another layer, making it larger and heavier. But eventually, the snowball becomes so big that it begins to crack beneath its own weight. Instead of growing smoothly, pieces start breaking away. Nature often works this way. Growth is rarely unlimited. Trees cannot grow forever. Mountains eventually erode. Even clouds become so heavy with water that they must release rain. For a long time, astronomers believed stars followed a similar rule. The universe certainly produces stars of many different sizes. Some are small, cool, and quiet, burning their fuel so slowly that they may continue shining for trillions of years. Others are brilliant blue giants that blaze through their lives in only a few million years before ending in spectacular explosions. Yet there seemed to be a natural ceiling, not because someone had written a cosmic rule saying, "No star may grow larger than this." Instead, the limit appears to emerge from a delicate balance between two powerful forces. One force is gravity, the other is light itself. That may sound surprising. We usually think of light as something gentle. Sunlight warms your face on a pleasant afternoon. A lamp quietly fills a room. Moonlight paints silver reflections across calm water. But light also carries momentum. Although each individual particle of light is extraordinarily tiny, an unimaginably large number of them pouring outward every second can exert a real pressure. Imagine trying to inflate a balloon while someone gently presses inward with both hands. As long as your breath is stronger than the pressure from outside, the balloon grows. If the pressure pushing inward becomes stronger, the balloon stops expanding. A massive star experiences a similar contest every moment of its life. Gravity constantly pulls its enormous mass inward. Meanwhile, deep within the star's core, nuclear fusion releases extraordinary amounts of energy. That energy races outward as light and heat, creating an outward pressure that resists gravity's relentless pull. A star survives because these two influences remain almost perfectly balanced. If gravity were suddenly stronger, the star would begin collapsing. If the outward pressure became too strong, the star's outer layers could be pushed away into space. For the overwhelming majority of stars, nature maintains this balance with remarkable precision. But what happens when a newborn star keeps gathering more and more gas? As its mass increases, the pressure and temperature in its core climb ever higher. Fusion becomes more intense, the star shines more brightly, and that increasing brightness produces even greater outward pressure. Eventually, astronomers expect the star to reach a point where its own light begins pushing away the very gas that is trying to fall inward. Instead of continuing to grow, the star effectively starts blowing away its future food. Astronomers refer to this natural threshold as the Eddington limit. It is not a rigid wall, rather it is a balance point, a region where adding more mass becomes increasingly difficult because the star's own brilliance begins resisting further growth. For many years, this idea suggested that stars should rarely become much more than about 100 to perhaps 150 times the mass of our own Sun. That expectation seemed perfectly reasonable. Then nature offered another surprise. Deep inside the Tarantula Nebula, a vast region of star formation in a neighboring galaxy called the Large Magellanic Cloud, astronomers found an extraordinary object known as R136A1. Instead of fitting comfortably within earlier expectations, this remarkable star appeared to possess a mass estimated at well over 200 times the mass of our Sun during its earliest stages. Even today, after losing tremendous amounts of material through powerful stellar winds, it remains one of the most massive stars ever identified. Immediately, a fascinating question emerged. Had astronomers misunderstood the limit, or had this star reached such an enormous size through an entirely different path? One possibility is that it was never truly born this large. Imagine two rivers slowly flowing toward one another. Eventually they merge, forming a single, broader current. Something similar may happen inside extremely crowded star clusters. In these dense stellar nurseries, young stars orbit surprisingly close together. Occasionally, two massive stars may collide or gradually merge, creating one even larger star. If this idea is correct, some of the universe's largest stars may actually be cosmic survivors of multiple mergers rather than single objects that grew uninterrupted from birth. Another possibility is that conditions in the early universe were dramatically different from those we observe today. When the first generation of stars formed, the cosmos contained almost nothing except hydrogen and helium. Elements such as carbon, oxygen, silicon, and iron had not yet been forged inside earlier generations of stars. Without those heavier elements helping clouds cool and fragment into many smaller pieces, enormous reservoirs of gas may have collapsed into just a few exceptionally massive stars. These ancient pioneers, known as Population 3 stars, have never been observed directly, yet many astronomers believe they were among the largest stars the universe has ever produced. If they truly existed, they may have lived only briefly before exploding or collapsing into the first generation of black holes, planting the seeds for even greater mysteries still waiting ahead. Because if stars that enormous seem difficult to explain, they may have created something even more astonishing, objects that swallowed light itself, objects that somehow became unimaginably massive while the universe was still in its cosmic childhood. And that mystery may prove even more challenging than the giant stars that came before it. If giant stars seem extraordinary, they may simply be the opening act for something even stranger. Every massive star lives with a quiet certainty. No matter how brilliant it shines, no matter how fiercely it burns, its supply of nuclear fuel is limited. One day, the delicate balance between gravity pulling inward and energy pushing outward begins to fail. The star has reached the end of its story. For smaller stars, the ending is gentle. They slowly shed their outer layers, leaving behind a dense white dwarf that gradually cools over billions of years. But the largest stars experience a far more dramatic fate. when the core can no longer support its own immense weight, gravity suddenly takes control. The collapse happens in an astonishingly short time, and the resulting explosion can briefly outshine an entire galaxy. What remains afterward may be one of the most extraordinary objects in nature, a black hole. The name itself often brings to mind images of giant cosmic vacuum cleaners, swallowing everything around them without mercy. The reality is both quieter and more fascinating. Imagine replacing our Sun with a black hole of exactly the same mass. Surprisingly, Earth's orbit would remain almost unchanged. Our planet would continue circling in nearly the same path. We would lose sunlight and warmth, but not because the black hole had suddenly pulled us inward. Gravity depends primarily on mass, not on whether that mass is a glowing star or a black hole. What makes a black hole remarkable is not that its gravity is magically stronger, it is that an enormous amount of matter has been compressed into an extraordinarily tiny region of space. Close enough, nothing, not even light, can escape. Yet black holes are not born gigantic. Most begin their lives with only a few times the mass of our Sun. That may sound impressive, but compared with the monsters found at the centers of galaxies, these newborn black holes are merely tiny seeds. Imagine planting an acorn. Years later, it becomes an oak tree. Given enough centuries, it grows thicker, taller, and stronger. Growth takes time. The same principle seems natural for black holes. As gas drifts nearby, gravity pulls some of it inward. Before disappearing forever, this falling material spirals into a rapidly rotating disk around the black hole. Friction inside that disk heats the gas to extraordinary temperatures, causing it to glow brilliantly before finally crossing the point of no return. Ironically, some of the brightest places in the universe exist immediately outside one of its darkest objects. But there is an important limitation. Imagine trying to keep a campfire burning by continuously adding wood. If you throw in one small log at a time, the fire happily consumes it. If you suddenly dump an entire truckload on top, the fire cannot burn everything instantly. The process has a natural pace. Black holes appear to have a similar limitation. As more gas falls inward, the surrounding disk grows brighter. That brilliant light pushes outward against newly arriving material, slowing the rate at which fresh gas can continue falling toward the center. Astronomers therefore expected black holes to grow steadily, but not infinitely fast. For decades, this picture seemed perfectly reasonable. Then telescopes began looking farther into the distant universe than ever before. Because light takes time to travel, looking deeper into space also means looking backward through time. A galaxy located billions of light-years away is not being observed as it exists today. It is being observed as it existed billions of years ago, when its light first began its long journey across the cosmos. Eventually, astronomers discovered something astonishing. Some of the earliest galaxies already contained supermassive black holes weighing hundreds of millions, or even billions, of times the mass of our Sun. Even more surprising, these objects already existed when the universe was only a few 100 million years old. On a cosmic calendar spanning nearly 14 billion years, that is astonishingly early. Imagine visiting a newly built city only a few months after construction began. You expect to see scattered houses, unfinished roads, and empty lots. Instead, you discover soaring skyscrapers, busy highways, sprawling neighborhoods, and a skyline rivaling cities that have existed for centuries. Your first question would not be, did someone break the laws of architecture? It would be much simpler, how did they build all of this so quickly? Astronomers found themselves asking exactly the same question. This challenge has become known as the growth time problem. If black holes began as ordinary stellar remnants and grew at the expected pace, many calculations suggest there simply was not enough time for them to become so enormous, so early in cosmic history. Something appears to be missing from the story. Perhaps the first black hole seeds were already much larger than we once imagined. Perhaps they occasionally fed faster than our simplest models allow. Or perhaps the early universe provided conditions unlike anything we observe today. One particularly intriguing possibility is known as direct collapse. Instead of beginning with a massive star that later collapsed, enormous clouds of gas may, under very special conditions, have avoided forming stars altogether. Imagine baking bread. Normally, the dough separates into many smaller rolls before entering the oven. But if the dough somehow remained together as one enormous mass, the final loaf would be vastly larger than anything usually produced. Some astronomers wonder whether something similar happened in the young cosmos. Rather than fragmenting into thousands of individual stars, certain gigantic clouds of hydrogen may have collapsed almost directly into enormous black hole seeds. If this occurred, the starting point would already have been dramatically larger, making the later growth much easier to explain. It is a beautiful idea, elegant, simple, yet so far, it remains one possibility among several. The universe has not yet revealed which path it actually chose, and as observations continue to improve, the mystery grows even richer. Because the same ancient universe that produced these impossible black holes also contained objects shining so brilliantly that they could be seen across billions of light years. Those dazzling beacons are known as quasars, and they may hold some of the most important clues of all. Imagine standing on a quiet shoreline late at night. The sea is almost completely dark. The horizon disappears into blackness. Then, far away, a lighthouse slowly sweeps its beam across the water. For only a few brief moments, the light becomes visible before disappearing once again into the darkness. Even from many kilometers away, you notice it immediately. Not because the lighthouse is enormous, but because it is extraordinarily bright. Across the universe, quasars perform a remarkably similar role. Although they appear as tiny points of light through our telescopes, they rank among the brightest objects nature has ever produced. Some release more energy than entire galaxies containing hundreds of billions of stars. At first, this seems almost impossible. How could something smaller than a galaxy outshine the galaxy itself? The answer lies in a curious irony. A quasar is not bright because of the black hole hidden at its center. In fact, the black hole itself remains perfectly dark. The brilliance comes from everything that is desperately trying not to fall into it. Imagine pulling the plug from a bathtub. The water does not disappear instantly. Instead, it begins swirling faster and faster as it approaches the drain, forming a graceful spiral. Gas behaves in much the same way around a supermassive black hole. Rather than plunging straight inward, enormous clouds of hydrogen, dust, and other material begin orbiting at tremendous speeds. They form a vast rotating structure known as an accretion disk. Inside this disk, neighboring streams of gas constantly rub against one another. That friction generates extraordinary heat. The temperatures become so extreme that the gas begins glowing brilliantly across the electromagnetic spectrum, from radio waves to visible light, ultraviolet radiation, and powerful X-rays. It is rather like watching a blacksmith heat a piece of metal inside a forge. At first, the metal simply grows warm, then it begins glowing red. Soon it shines orange, then yellow, and eventually almost white with heat. The hotter it becomes, the more intensely it radiates. Around a quasar, the same principle unfolds on an almost unimaginable scale. The glowing material immediately surrounding the black hole becomes one of the brightest regions in the observable universe. Ironically, the darkness itself is almost invisible. It is the final moments before the gas disappears forever that illuminate the cosmos. For decades, astronomers regarded quasars as extraordinary but understandable consequences of supermassive black holes feeding on enormous supplies of gas. The general picture seemed elegant. Galaxies formed. Some developed central black holes. Gas gradually flowed inward. Those black holes occasionally became active, producing brilliant quasars. Everything appeared to fit together. Then astronomers looked farther into the past. Because light requires time to travel, every increase in telescope sensitivity allows us to observe an earlier chapter in cosmic history. Older telescopes revealed quasars that existed when the universe was perhaps 1 billion years old. Even those discoveries were surprising, but the James Webb Space Telescope soon pushed the frontier much farther. Instead of finding only a handful of bright, ancient quasars, Webb began revealing a young universe crowded with unexpected objects. Among the most intriguing are a population that astronomers have nicknamed the Little Red Dots. At first glance, these tiny reddish sources seemed almost insignificant. They looked far too compact to be ordinary galaxies, yet far too numerous to fit comfortably into previous expectations. Some may represent extremely young galaxies packed with stars. Others may conceal rapidly growing black holes hidden beneath thick blankets of gas and dust. The scientific community is still debating exactly what they are. That uncertainty is part of what makes them so exciting. Nature has presented us with another puzzle before offering the solution. Around the same time, astronomers also identified another surprising population, sometimes called the blue monsters. Unlike the dusty red objects, these appear remarkably bright and energetic, suggesting black holes consuming matter at astonishing rates during the universe's earliest epochs. Taken together, these discoveries paint a picture very different from the simple one astronomers once imagined. Rather than a quiet young cosmos slowly assembling itself over immense stretches of time, the early universe now appears vibrant, dynamic, and astonishingly productive. Galaxies were forming, stars were igniting, black holes were growing, sometimes all at once. It is almost as though we expected to arrive at dawn and discover only the first faint colors of sunrise. Instead, we found bustling cities already awake, with lights shining from every window. Naturally, this raises an important question. If quasars were already blazing so brilliantly, only a few 100 million years after the Big Bang, what powered them? Were their black holes born unusually massive? Did they somehow consume matter far faster than current models predict? Or are we still overlooking an important piece of the physics governing the young universe? No single answer has yet emerged. Instead, astronomers continue testing many possibilities. Some simulations suggest that dense reservoirs of gas could temporarily feed black holes much faster than once believed. Others explore whether unusually massive seed black holes formed through direct collapse, giving quasars a substantial head start. Still others examine whether dust, magnetic fields, or complex gas dynamics behave differently under the extreme conditions of the early cosmos. Each new observation narrows the possibilities. Each new discovery reshapes the questions. That is the quiet beauty of science. The goal is not to protect old ideas from change. The goal is to let nature reveal the truth, even when it surprises us. And as extraordinary as these ancient quasars appear, they are still individual objects. The next mystery becomes larger still, so large in fact that it stretches across hundreds of millions of light years, forcing astronomers to ask whether the very architecture of the universe is as simple as we once believed. Until now, every mystery we have explored has shared something in common. Each one involved an individual object, a giant star, a rapidly growing black hole, a brilliant quasar. Extraordinary as they are, each can still be imagined as a single character playing its part upon the enormous stage of the universe. Now, however, we gently pull the camera farther back, far beyond individual stars, far beyond galaxies, far beyond even clusters of galaxies, and as the view expands, something remarkable begins to emerge. The universe is not arranged randomly. If every galaxy were represented by a tiny point of light, you might expect those points to be scattered almost evenly across space, rather like grains of sand tossed across a floor. Instead, something very different appears. Imagine looking at morning dew resting upon a spider's web. The tiny droplets do not float independently. They collect along delicate strands, outlining a pattern that was almost invisible before. The galaxies of the universe behave in a surprisingly similar way. They gather along immense filaments, stretching across hundreds of millions of light years. Where several filaments intersect, enormous galaxy clusters form, vast cities of the cosmos containing hundreds or even thousands of galaxies bound together by gravity. Between these luminous highways lie enormous empty regions called cosmic voids. Some are so large that a beam of light requires hundreds of millions of years simply to cross them. Rather than resembling a uniform fog, the universe begins to look like an intricate network. Astronomers call this immense architecture the cosmic web. It is one of the most beautiful discoveries of modern cosmology. Its structure did not arise because someone carefully arranged galaxies into neat patterns. Instead, it emerged naturally over billions of years as gravity gently amplified tiny differences that already existed shortly after the Big Bang. Imagine rainwater flowing across a hillside. At first, the water spreads almost evenly. Soon, tiny channels begin to appear. Those channels merge into streams. Streams join rivers. Eventually, an entire landscape develops, shaped by nothing more than gravity, acting patiently over time. The cosmic web formed in much the same way. Invisible halos of dark matter provided the underlying framework. Ordinary matter gradually flowed into those gravitational valleys, giving birth to galaxies and galaxy clusters. Computer simulations reproduce this remarkable process with astonishing success. When astronomers compare simulated cosmic webs with observations from the real universe, the resemblance is often breathtaking. For many years, this agreement strengthened confidence in one of cosmology's most important assumptions. It is known as the cosmological principle. The idea itself is surprisingly simple. Imagine flying high above Earth. Individual houses disappear, entire neighborhoods blend together. Eventually, even cities become difficult to distinguish. From sufficiently far away, the landscape begins to appear fairly uniform, despite containing countless local differences. The cosmological principle suggests something similar about the universe. On relatively small scales, galaxies gather into clusters. Clusters join filaments. Voids separate them. But on sufficiently enormous scales, these variations should average out. No region should remain fundamentally special. The universe should appear statistically similar in every direction. This assumption is woven deeply into nearly every modern cosmological model. It allows astronomers to describe the evolution of the entire universe using remarkably elegant mathematics. Then observations revealed something unexpected. Among the earliest surprises was a colossal structure known as the Sloan Great Wall. Discovered during the Sloan Digital Sky Survey, this immense collection of galaxy clusters and filaments stretches across roughly 1.5 billion light-years. Its sheer size immediately captured astronomers' attention, yet even larger candidates would eventually emerge. One particularly intriguing discovery became known simply as the giant arc. Rather than forming an ordinary filament, this immense arrangement of galaxies appears to trace an enormous curved structure extending across more than 3 billion light-years. If confirmed exactly as interpreted, it would rank among the largest known structures in the observable universe. Not long afterward came another remarkable candidate, the giant quasar group. Instead of galaxies alone, this structure contains dozens of quasars, apparently associated across astonishing cosmic distances. Its estimated dimensions approach 4 billion light-years. Numbers like these are difficult to picture. Imagine shrinking our entire Milky Way galaxy to the size of a grain of sand. Even then, these enormous structures would remain almost unimaginably large by comparison. Naturally, astronomers began asking an important question. Are these truly single structures? Or are our eyes simply connecting patterns that only appear meaningful because of the limited information available? Humans are remarkably talented at recognizing patterns. Sometimes that ability serves us beautifully. Sometimes it leads us astray. You have probably looked at clouds and noticed familiar shapes. A sailing ship, a rabbit, a mountain range. The clouds themselves never intended to create those images. Our brains assembled them naturally. Astronomers must remain equally cautious. Whenever exceptionally large cosmic structures are reported, researchers immediately begin testing whether statistical chance, observational bias, or incomplete surveys could produce similar patterns. Many proposed giant structures become less convincing as additional observations accumulate. Others appear increasingly robust. The scientific discussion continues. This careful skepticism is not a weakness. It is one of science's greatest strengths. Extraordinary claims demand extraordinary evidence. Only after years of independent observations, improved surveys, and repeated analysis do astronomers gradually decide whether a discovery truly reshapes our understanding of the universe. At present, the situation remains wonderfully open. Some cosmologists believe these immense structures still fit comfortably within existing models. Others argue that their sizes may hint at subtle gaps in our understanding of cosmic evolution. No consensus has yet emerged. And perhaps that uncertainty is exactly what makes these discoveries so captivating. The universe has not handed us a finished puzzle. Instead, it has quietly placed a handful of unexpected pieces on the table, inviting us to reconsider the picture we thought we understood. The next question, however, reaches even deeper. If these remarkable stars, ancient black holes, brilliant quasars, and colossal structures all seem unexpectedly difficult to explain, what do they actually have in common? Why does nature keep producing objects that appear to stand so close to the boundaries of possibility? That mystery will guide the next stage of our journey. By now, you may have noticed a quiet pattern emerging. Every mystery we have explored shares the same underlying question. Not simply, how did this object form? But rather, why was nature able to build something so large in the first place? That distinction matters. Astronomers are not surprised that stars exist. They are not surprised that black holes exist. Nor are they surprised that galaxies gather into enormous networks. The surprise comes from how close some objects appear to the limits that physics itself seems to impose. Imagine an architect designing a skyscraper. The taller the building becomes, the greater the stress placed upon its foundations. Wind exerts larger forces. Materials bend under increasing weight. Elevators become more complicated. Even carrying construction materials to the upper floors becomes increasingly difficult. None of these challenges suddenly appears at the last moment. Each one grows gradually. Eventually, every additional floor becomes harder to build than the one before. Nature faces similar challenges. Whenever the universe tries to build something exceptionally large, several different physical processes begin pushing back. The remarkable thing is not that limits exist. The remarkable thing is that nature repeatedly finds ways to approach them. Consider once again a giant molecular cloud, the birthplace of stars. These immense clouds may contain enough gas to create hundreds of thousands of stars. At first, it might seem obvious that such a cloud should simply collapse into one enormous object. Gravity certainly tries to do exactly that. But gravity is not working alone. Inside the cloud, tiny disturbances begin growing. Some regions become slightly denser than others. Denser regions attract even more gas. Soon, instead of forming one gigantic star, the cloud begins breaking apart into many smaller clumps. Astronomers call this process fragmentation. An everyday loaf of bread offers a surprisingly useful comparison. Imagine preparing a large piece of dough. If everything remains perfectly smooth, you could bake one enormous loaf. But as the dough rises, pockets form throughout it. Those small instabilities change the final shape. Similarly, a giant cloud of gas rarely remains perfectly uniform long enough to collapse into a single star. Instead, it naturally divides itself into many separate stellar embryos. Fragmentation is one of nature's favorite ways of preventing extremes. Even when a particularly massive star does begin forming, another obstacle soon appears. The newborn star starts shining. At first, its light is relatively gentle, but as nuclear fusion accelerates inside its core, the star becomes astonishingly luminous. That intense radiation does more than illuminate surrounding space. It pushes. Imagine trying to sweep dry autumn leaves into a neat pile, while someone continuously blows a powerful fan across the yard. Each time the pile grows larger, the wind scatters the leaves once again. Massive young stars behave in much the same way. Their ultraviolet radiation heats nearby gas, while stellar winds blast enormous quantities of material outward at millions of kilometers per hour. Astronomers refer to these effects collectively as stellar feedback. Ironically, the very star that is trying to grow begins destroying its own food supply. The brighter it becomes, the more effectively it prevents additional gas from falling inward. Once again, nature creates a self-regulating system. Growth encourages resistance. Resistance slows growth. Black holes encounter a surprisingly similar difficulty. Although they seem capable of swallowing almost anything, feeding them efficiently is far more complicated than popular imagination suggests. Gas falling toward a black hole does not simply disappear. Before crossing the event horizon, it becomes extraordinarily hot. The resulting radiation pushes outward against newly arriving material. Too much infalling gas actually generates enough energy to make continued feeding more difficult. Imagine traffic entering a busy city through a single highway. Adding more cars initially increases the flow. Eventually, congestion appears. Soon, the very process of increasing traffic begins reducing the overall speed. Black hole growth seems to obey an analogous principle. For sustained periods, there appears to be a practical upper rate at which matter can fall inward. Yet some of the earliest supermassive black holes appear to have reached extraordinary masses despite this apparent bottleneck. That is why astronomers continue searching for circumstances under which these limits may temporarily relax. Perhaps dense gas clouds occasionally overwhelmed the normal feedback. Perhaps magnetic fields redirected material more efficiently. Perhaps short episodes of unusually rapid growth occurred before equilibrium returned. None of these possibilities violates known physics. Instead, they explore regions where familiar physics behaves under extraordinarily unfamiliar conditions. The same pattern continues on even larger scales. Galaxies do not instantly gather into colossal walls stretching billions of light-years. Gravity requires time. Small structures merge into larger ones. Groups become clusters. Clusters connect through filaments. This gradual assembly is known as hierarchical structure formation. Like villages growing into towns and towns growing into cities, cosmic architecture develops step by step across billions of years. When astronomers encounter structures that appear exceptionally large for the available cosmic time, they naturally ask whether those structures genuinely challenge existing models or whether our observations are still incomplete. This distinction is important. Science advances by questioning observations as carefully as it questions theories. A surprising discovery may represent a revolutionary breakthrough, or it may reveal subtle biases in how we collect data. Neither possibility is disappointing. Both teach us something valuable. Perhaps that is the deepest lesson hidden inside all these cosmic monsters. The universe is not a machine built to satisfy our expectations. It simply exists, patiently, quietly, following rules that remain the same whether humans understand them or not. Every generation of astronomers inherits a map drawn by those who came before. Every generation also discovers that the map is unfinished, not because earlier explorers failed, but because the landscape extends farther than anyone previously imagined. And so, Rather than asking whether physics has broken down, astronomers increasingly ask a gentler question. Have we finally reached the edge of our current understanding? Or are we standing at the beginning of an entirely new chapter? The answer may already be taking shape inside the next generation of telescopes, simulations, and observations, offering ideas that once seemed impossible, but which are slowly becoming part of the scientific conversation. One of the most comforting aspects of science is that mysteries are not signs of failure, they are signs that discovery is still alive. When astronomers encounter an object that seems impossible, they do not immediately conclude that the laws of physics have broken down. Instead, they begin asking a quieter question: what have we not yet considered? That simple question has guided scientific progress for centuries. Sometimes the answer is surprisingly small, a measurement that becomes more accurate, a calculation that includes an overlooked effect, or an observation that reveals a hidden detail. At other times, the answer requires an entirely new perspective. The cosmic monsters we have explored tonight have inspired exactly this kind of careful thinking. Not a search for magical explanations, not a desire to discard everything we already understand. Rather, a patient effort to discover whether familiar physics, operating under unfamiliar conditions, can naturally produce extraordinary results. One of the first ideas begins with an observation that seems almost obvious once it is stated. Perhaps some black holes simply started much larger than we originally imagined. Imagine two runners competing in a marathon. One begins at the official starting line. The other quietly begins 20 kilometers farther along the course. Hours later, both cross the finish line. If you looked only at the ending, you might conclude that the second runner possessed impossible speed. In reality, the race began from a different starting point. Some astronomers suspect the earliest supermassive black holes may have enjoyed a similar advantage. Instead of forming from ordinary stellar remnants weighing only a few dozen times the mass of our Sun, they may have originated from direct collapse black holes containing hundreds of thousands of solar masses almost from the beginning. Under this hypothesis, enormous clouds of pristine hydrogen collapsed so rapidly that they bypassed the normal stage of forming countless individual stars. Such conditions would have been exceptionally rare. The early universe was not filled with these giant seeds, but it may not have needed very many. A handful of unusually massive beginnings could eventually grow into the billion solar mass giants observed by the James Webb Space Telescope and other observatories. Another possibility looks not at the beginning of the journey, but at the pace of growth itself. Earlier, we explored how radiation normally slows the feeding of black holes. This balance produces what astronomers often describe as the Eddington limit, a practical guideline for sustained growth. Yet, nature rarely insists that every process remain perfectly steady. Imagine a river after weeks of gentle rainfall. Its flow is calm and predictable. Now imagine a sudden mountain storm. For a short time, enormous torrents of water rush downstream, carrying far more material than the river usually transports. Eventually, the current settles once again. Some researchers believe black holes may occasionally experience similar bursts. Brief periods of super-Eddington accretion could allow matter to fall inward much faster than the average rate predicted by simpler models. These episodes would not continue forever. The powerful radiation produced by the inflowing gas would eventually restore equilibrium, but even relatively short bursts, repeated many times over millions of years, could dramatically accelerate growth. Computer simulations increasingly suggest that such episodes are physically plausible under particular conditions. The universe, it seems, may occasionally feed its black holes in sudden feasts rather than steady meals. Then there are the stars themselves. Earlier we met the hypothetical population 3 stars, the first generation of stars ever born. Because the young universe contained almost no heavy elements, these pioneers may have grown far larger than the stars we observe today. Some models suggest that after only a few million years, these enormous stars collapsed directly into unusually massive black holes. Although still much smaller than the giants at the centers of galaxies, they would have provided significantly larger seeds from which later growth could begin. Yet another proposal is even more imaginative. It introduces an object that has never been observed directly, but which emerges naturally from certain theoretical calculations. These are known as dark stars. Despite the name, they are not black holes, nor are they invisible. Instead, they are hypothetical stars powered, at least in part, not by ordinary nuclear fusion, but by interactions involving dark matter. If such objects briefly existed in the earliest universe, they may have grown to extraordinary sizes before eventually collapsing into unusually massive black holes. The idea remains speculative. Many astronomers remain cautious. Even so, it demonstrates the remarkable creativity with which science explores every possibility permitted by known physics. Not every promising idea survives future observations. That is precisely how science works. Equally important are the tools used to test these ideas. Modern astronomy no longer relies solely on telescopes. Some of its most powerful discoveries emerge inside vast computer simulations. Imagine trying to understand how an entire forest grows. Watching a single tree is not enough. You must also understand changing weather, flowing rivers, shifting soil, countless species of plants, and the interactions connecting them all. The universe presents an even greater challenge. Researchers now build enormous numerical simulations containing billions of particles representing dark matter, gas, stars, and galaxies. These virtual universes evolve according to the same physical laws believed to govern the real cosmos. When simulated galaxies begin resembling those observed through telescopes, confidence in the underlying models grows. When they do not, astronomers learn where improvements may still be needed. Sometimes the universe itself also plays unexpected tricks on observers. Not every astonishing discovery turns out to be exactly what it first appears. Imagine looking through an old window whose glass bends light slightly. Objects beyond the glass may appear stretched, brighter, or distorted. The universe contains its own version of this phenomenon. It is called gravitational lensing. Massive galaxies and galaxy clusters curve space itself, bending the paths followed by light from more distant objects. This natural magnification can make remote galaxies appear brighter than they truly are, allowing astronomers to detect objects that would otherwise remain invisible. At the same time, it can complicate estimates of their true sizes, luminosities, or distances. Careful analysis is therefore essential before any extraordinary claim becomes an accepted discovery. Observational bias also plays an important role. Every telescope has limits. Every survey examines only part of the sky. Every instrument favors certain wavelengths over others. Like assembling a puzzle with many missing pieces, astronomers must always remember that today's picture remains incomplete. And perhaps that is the most reassuring conclusion of all. None of these ideas asks us to abandon gravity. None requires rewriting quantum physics. None demands that the universe behave magically. Instead, they remind us that nature often proves richer than our first models, more subtle than our earliest assumptions, and more patient than our imagination. Each new telescope extends our vision a little farther. Each new simulation fills another blank space on the map. Each new discovery transforms one mystery into the beginning of the next. And with every step, the cosmic monsters become a little less frightening, not because they are becoming smaller, but because they are slowly becoming understandable. As our journey gently draws toward its end, it is worth pausing for a moment to appreciate just how remarkable this story truly is. When astronomers first began carefully studying the heavens, the stars appeared fixed and eternal. The night sky looked calm, orderly, predictable. Today, that same sky tells a very different story. Behind every quiet point of light lies a universe of motion. Stars are born from cold clouds of gas. Galaxies collide over billions of years. Black holes quietly reshape the hearts of galaxies. Invisible dark matter weaves an immense cosmic framework that stretches farther than human imagination can comfortably picture. The universe is not still. It has never been still. It is always becoming. Throughout tonight's journey, we have met objects that seem almost too extraordinary to be real. Stars whose brilliance pushes against the limits imposed by their own light. Black holes that appear to have grown up long before they should have had enough time. Quasars whose radiance crossed nearly the entire observable universe before eventually reaching the mirrors of modern telescopes. Structures stretching across billions of light years, hinting that the architecture of the cosmos may still hold secrets waiting to be uncovered. At first, these discoveries can feel unsettling. After all, we often imagine science as a collection of answers, but perhaps science is better understood as something else. Imagine reading a wonderfully written novel. Every chapter answers certain questions while quietly introducing new mysteries. The story never becomes smaller as you continue reading. It becomes richer, more connected, more beautiful. The universe behaves in much the same way. Every discovery resolves one uncertainty while revealing another horizon just beyond it. That endless unfolding is not a weakness of science. It is its greatest strength, because the goal of science has never been to protect certainty. Its purpose is to follow evidence wherever nature chooses to lead. Sometimes that journey confirms what we expected. Sometimes it surprises us completely. Yet both outcomes move understanding forward. Perhaps that is why astronomers often speak with such quiet excitement whenever observations disagree with prediction. A disagreement is not necessarily bad news. Quite the opposite. It often marks the place where discovery is about to begin. History reminds us of this again and again. The expanding universe, the existence of galaxies beyond the Milky Way, neutron stars, black holes, gravitational waves, planets orbiting distant stars. Each of these ideas once seemed speculative. Some even appeared impossible. Today they form part of our ordinary understanding of the cosmos. It is entirely possible that some of today's mysteries will one day seem equally familiar. Future observatories are already preparing to continue the search. New generations of giant telescopes will soon observe the earliest galaxies with even greater detail. Space missions will measure the distribution of dark matter more precisely than ever before. Powerful computer simulations will recreate increasingly realistic universes, allowing researchers to compare theory with observation in extraordinary depth. Each instrument becomes another lantern carried into the darkness. Not because the darkness is something to fear, but because every small circle of light reveals another unexpected landscape. There is something quietly humbling about this. Our species occupies a tiny planet, orbiting an ordinary star near the edge of one fairly typical galaxy. We have existed for only a brief moment compared with the age of the cosmos, and yet, through patience, mathematics, imagination, and careful observation, we have learned to reconstruct events that occurred billions of years before Earth itself had even formed. That achievement is remarkable, not because humans are unusually important, but because the universe appears willing to be understood. Its laws remain consistent across unimaginable distances. The same gravity that guides a falling leaf also shapes entire galaxies. The same atoms within your body were forged inside ancient stars whose light disappeared long before our solar system came into existence. In a very real sense, you are connected to the story we explored tonight. The iron carried through your bloodstream, the calcium inside your bones, the oxygen filling your lungs. Every one of those atoms once belonged to earlier generations of stars. Long before there were people wondering about the universe had already begun preparing the ingredients that would eventually allow someone to ask the question, Perhaps that is the gentlest mystery of all. The cosmos has spent nearly 14 billion years evolving remarkable structures. Stars, planets, galaxies, and immense webs of matter stretching across incomprehensible distances. Somewhere along that journey, tiny living creatures emerged on one small world. Eventually, one species looked upward, not in search of food, not to escape danger, but simply to understand. And perhaps the universe's greatest monsters are not frightening because they are enormous. Perhaps they are inspiring because they remind us that reality is always larger than our imagination. They encourage humility without diminishing wonder. They invite curiosity without demanding certainty. And they quietly remind us that every answer is also the beginning of another question. As the night grows quieter and the stars continue their slow journey across the sky, you can let these thoughts drift gently through your mind like distant constellations. There is no need to solve every mystery tonight. The universe has waited billions of years. It will still be there tomorrow, and tomorrow, patient observers will continue listening to the faint whispers carried across space and time, adding another small piece to the endless story written among the stars. For now, you can simply rest beneath that vast cosmic ocean, comforted by the thought that wonder does not disappear when questions remain unanswered. Sometimes wonder grows precisely because they do. So wherever you are tonight, whether you are still listening, quietly reflecting, or already beginning to drift towards sleep, I hope this journey has left you with a peaceful sense of perspective. The stars will continue shining, the galaxies will continue turning, the universe will continue revealing itself, one gentle discovery at a time. And until our next journey together, may your night be calm, your dreams be filled with quiet wonder, and your rest be as deep and peaceful as the ancient cosmos itself. Good night.